So welcome everyone to my talk about fat-free data center networks. So over the past few months I've been collaborating with Ankit and with Asaf, Gal and Michael here at Hebrew University, specifically interested in creating cost-efficient data center networks, which are aimed at addressing the skewed traffic scenario within data centers. So within a data center, it's relatively common to have a few TORs or a few racks which are very hotspots in terms of traffic. A recent study by Microsoft has shown that 46 to 99% of the rack pairs within the data center exchanges no traffic at all, which really highlights how skewed of a case it is within a data center. So creating fully non-blocking interconnects, which are extremely expensive, in this skewed case makes no sense. It's expensive and you barely use any part of the network. So how can we then adapt this part to create, to accommodate for skewed, but still be able to create cost-efficient networks? So let's zoom into the fat tree. So let's say that we oversubscribe the fat tree. We remove 25% of the capacity and removing one of the core nodes at the top. This means that we are left with 75% of the network capacity. But let's say that we only have two pods communicating, which translates to 50% of the servers. These 50% of servers are only able to achieve 75% of the network capacity between those two, even though only 50% of the servers are active. This would mean that basically these three links become the bottleneck between the communication of these two pods, and the rest of the network remains idle and cannot be used for any additional routing. So this body of research has, of course, it has been identified, and there has been over a decade of work in this field. It increases with higher scale fat trees. So let's say that you have a KS96 fat tree, a very large fat tree, not that uncommon at this scale. So let's say we build at 75% of the capacity, and we only have two pods active within the network. These two pods, or this 2%, is only able to achieve 75% of the amount of communication that they can put into the network. And this only increases when you have higher oversubscription, let's say 25%. So this has been identified, and to address these skewed traffic scenarios, it has been proposed to use dynamic topologies. Dynamic topologies, for example, bounce lasers off the ceiling to create connections ad hoc, or use wireless connections or directed radio waves to create, to address this skewness. So instead of using wired connections. So let's generalize this. So we have a topology adaptation network in which we have two hotspots which are active. These hotspots are then connected with dynamic links, and these dynamic links can then serve the traffic skewness between these two hotspots. To generalize this, to give like a model, we assume that any dynamic interconnect is a dynamic topology which can have a fixed network degree for every top of rack. These networks, although they are very appealing and they address the question of skewness, have a set of novel challenges, such as that you have to, if you have lasers, you have to align the top of rack switches correctly, such that the lasers land on the receivers, or environmental factors such as dust and vibration. But this gives a rather challenging approach. So it's an intuitive, appealing idea, but what is very interesting to also look at, and in our research, is that at the moment there's a lack of rigorous benchmarks. You want to quantify how much every network is able to address this skewed traffic scenarios. Furthermore, fat trees themselves are a very easy baseline. As I've shown, the oversubscribed fat trees are very poor in handling these skewed cases and are an easy target. Furthermore, so far it has not been identified what are actually the foundational answers to the questions of dynamic links, and I will go into each of these 3 points. So let's take a flexible network. So we want to address how can we quantify the flexibility within a network. So on the x-axis we have the fraction of servers which are active, so the skewness in a way, and on the y-axis we have the amount of throughput per server. Let's say that we are able to achieve alpha throughput per server, or alpha fraction throughput per server, as an all-to-all, or well, when all servers are active, not necessarily an all-to-all. So then, let's say that we only have alpha of the servers active, so alpha fraction of the servers themselves are active, so a more skewed case. In this case, we will want to have the network to achieve full throughput between only that select amount of few. And between these 2 points, we would like a graceful decline in performance, such that when only a few servers themselves are active, it's able to achieve high throughput, and when more and more servers become active, it decreases proportional. As such, we name this metric throughput proportionality, and it expresses the desire to handle skewed traffic scenarios. So fat trees themselves are actually ideal inflexible. They are at an alpha's oversubscribed fat tree is very far from the metric and very far from the ability to handle skewed workloads. So I've now told you what doesn't work, so fat trees or as such in trees. So what we propose are deploying near optimal expander graphs as the solution to this problem. So these expander graphs are the racks themselves, or the TORs, are directly connected to other TORs. As such, you have a flat pool of connectivity. What makes this appealing, and of course other topologies have also been proposed that have a flat pool of connectivity, is that the expander graph has extremely nice properties such that every subset of nodes is very well connected to any other subset of nodes with high likelihood. So now this basically poses a fundamental question. What's the value of being able to dynamically move links around at a higher cost for every link, against having a flat pool of connectivity, for example the expander graph, which has lower cost links? So how valuable is the ability to move links around? So to quantify this, we did a optimal flow comparison. So again, on the x-axis we have the fraction of servers with traffic demand, so skewness. On the y-axis we have the amount of throughput attained per server. So the fat tree is able to achieve this level of performance. The dynamic network, at an equal cost point as the fat tree, is able to achieve a significantly higher amount of throughput per server, as has been indicated by the body of research so far. The expander, which is at the equal cost point, is able to achieve a higher amount of throughput in the region that we care about, because only a very small fraction of servers are active in a data center has been shown. So like 46 to 99% of the rack pairs exchanged no traffic at all. To highlight the throughput proportionality, or the idea of having a graceful decline, is that the expander graph itself is relatively close to the desire of having throughput proportionality. So I've now been talking about expanders, and let's give a toy example. So on the left-hand side we have a fat tree, which is oversubscribed, is double oversubscribed, and has 20 nodes. On the right-hand side we have an expander with 16 nodes, and the expander is built at 80% of the cost, so it has 80% of the nodes themselves. So let's introduce a skewed traffic matrix in which only 25% of the servers themselves are active. This means that these two nodes within the fat tree are active, and this translates in the expander to these 4 TORs. So the fat tree itself is nowhere near the full throughput. It's heavily bottlenecked here at the bottom, and it's only able to achieve 50% of the amount of traffic that the servers would want to put into the network. As such, these become the bottleneck in a very skewed case. In the case of an expander, it's able to achieve full throughput. As such, you can see that although routing has become more difficult, which we will address at the end of the talk, it is able to achieve 100% of the throughput or using less equipment and while supporting the same amount of servers. It's important to note that significant scale is needed for an expander to work properly, because for the graph properties to hold that come from graph theory, it's necessary to have a large amount of nodes to support the scale. So the next question is basically, so I've shown you expanders are a good solution. So how do we address deployment of these expanders? So you can see on the left-hand side, it seems very disorganized. You have only a flat pool of connectivity, there's no tree and so forth. But we've, especially here at HebrewU, has been significant progress in deploying these expander graphs and realizing them as a viable data center architecture, and there's some promising results towards the deployment of them. So finally, I would like to come to the routing part. So as you've seen within an expander, it doesn't necessarily mean that, like in a tree, you can only use shortest path routing. You have to be more clever. So let's take simple routing. So only simple routing, for example, using ECMP. So we only use shortest paths, which is very vulnerable to creating very specific bottleneck within the network, which would be undesirable, but has very low RTT, which is good for short flows. And on the other side, we have VLB. So basically, it means that you select a Valiant node and you do shortest path routing to that Valiant node, and then from the Valiant node, you go to the destination. What we propose is basically a hybrid between these two, in which you use ECMP until you reach a certain threshold queue, which is set to 100 kilobytes in our case, such that you accommodate for short flows. And afterwards, we move to VLB such that we don't create specific bottlenecks in the network. So we did a packet level simulation on this case for a rather common workload, a skewed workload. So on the x-axis, again, we have the amount of load that's put into the network. And on the y-axis, we have the average flow completion time. So a lower flow completion time is better. The FAT3 performance using ECMP. Then we have the expander, which uses ECMP. You can see that at low load, only using ECMP, so shortest paths, is a viable option, but it very quickly creates bottleneck. As such perform poorer than the FAT3 specifically. And the expander using hybrid, and specifically because of the advantages of VLB, is able to achieve a performance similar to the FAT3. So with this, I would like to end my talk. So I would like to say that expanders are a promising development in data center architecture and could revolutionize the field, I would say. Thank you.
How do you know ahead of time which server will be hot?
Actually, so you don't know ahead of time which server will be hot. As such, so in a FAT3, you use a fully bandwidth interconnect, which is like the typical solution in this case. So for an expander, we also don't assume anything. You can take any nodes or any servers which will become hot, and because any subset of nodes it has guarantees such that it is very highly connected with each other, you can still achieve high throughput regardless where the TORs are active or where the servers are active.